you want to understand that it is always, in this case, by parts. Just that you want to choose your I and D carefully. And then there are some tricks in between, you know. Like in this question here, the trick in this question, if you can recall, is actually in here. So in this question, right, you need to know that you use this trick. In the earlier question, if you could recall, right, in the earlier question, we also have to use some tricks here. So these are some of the tricks that you want to remember. Otherwise, it can take forever, no? Of course, that may not be exhaustive. There could be others down the road that I probably have not seen myself, you know. Just that on the spot, you want to be able to be clever and come up with a workaround for a question like this. Okay? Then following this, there's actually a word example. You can actually read for yourself, you know, this word example. And the idea is the same, it's again by parts. Right? Yep. Yes. The other one, is it? Okay, let me show. Okay, so when you reach this line, the idea here is to rewrite this fella. Rewrite the x square. Rewrite the x square as 1 plus x square minus 1. The reason for doing so is like this, no, is because then when this term is multiplied to this term, right, you get this one. This is the trick. When you take this, right, to multiply with this, right, this whole thing, right, you get this one. Yeah, this is a trick. So that thing shows up. What thing shows up now? The IN will show up after that. You can see. It's a very clever trick. It's not rocket science. If you haven't seen before, it might struggle a bit. But now that you have seen it, next time it becomes second nature.
Oh my god.
Yeah.
Wait.
Okay. You want to jot down, is it? Sure. Let's wait for a moment for Aditi to jot down first. Okay. In the meantime, you can browse through that word example 23, you know. Is again by parts. Again, it demonstrates to you how clever math people are. Math, okay? To do well in biology, right? Or to do well in CS, you want to first and foremost do well in math. The head of department of math long ago, he said, you know, if you can do math, you can practically do everything under the sun, you know. I pondered for a little while when he said this. We were shown around because they bring us around the math department. That was in my honors year, I know. So he said this to the group of us. And after some thoughts about it, I think it's quite true. You know? Math, right, make you very flexible, stretches your mind quite a lot, you know. Yeah. So I think you can do math, you can practically do anything under the sun, you know. Because you get very strong logic, you see. Okay, Aditi, can I move on? Okay, so moving on, we're going to, okay, this one left to you to read for yourself. We are going to embark on, ta-da, something that you have sort of done it before in your lower year, right? You have already come across this term, Riemann sum. In fact, if I say left Riemann sum, you understand what I'm talking about, no? Let's hear from Ivan. Roughly, when we say left Riemann sum, what do we mean? Yeah, in rectangles, and the height of rectangle is taken as the height of the left side, right? And then there's also the right Riemann sum. And today we are going to repeat the same story again, using a concrete example. The example is y equals to x squared. So to start off with, I want to ask that you draw the line, or draw the curve y equals to x squared onto the left hand side. I am sure, I have no doubt about it that all of you can draw this graph. And the subject of interest in this portion here is to actually try to look at the area under the ground from 0 to 1. And as you have probably seen before, what we normally do is we will divide this into n rectangles. We divide this into rectangles. And we're hoping to actually find an approximate value for the area under the graph by looking at the area of the rectangles. How do you find the area of the rectangles? Okay, because you divide them into n equal parts, each part is therefore having a width of 1 over n. Okay, Ivan, what is the coordinates of this point? This will be n minus 1, and this one is actually n over n, right? Right. Okay, still Ivan, tell me how to find the area of the first rectangle, which is 1 over n the second area. Ivan? Right. How about the last rectangle? Right. And then you total them up. You total up all these areas. What will it be, Ivan? Huh? You mean n cube, right? And what's inside here? Okay, you must have the eyesight to be able to see that the total area turns out to be this summation. After taking out common factors of n and n squared, which is therefore n cubed on the denominator, you'll be left with 1 square plus 2 square plus 3 square until n square. And I'm almost sure Ashad can tell me off the cuff. Ashad, what is the formula for this summation? This summation of r equals 1 to n of, okay, I believe he can tell me off the cuff. Ashad, please.
I think it's r and r plus 1 and r plus 1.
Right. Why Ashad? Because Ashad is very familiar with series. No? Yeah.
Oh, yes, you remember.
Right. Long ago, there were the KSA student who, in fact, every year we have students from overseas who come visit us. No? So I remember KSA students are quite capable. This boy just came to the front and just wrote down the formula straight away. And then upon checking, like, I found that actually they also do math Olympiad in their own school. And it's one of the representative. Okay, so with this in mind, we will plug it in. We'll plug it in as if you plug it in and tidy up. Okay, this one need a bit of eyesight test, Need a bit of eyesight test. If you plug it in into the formula, okay, let me count, see how long the whole class takes to see, okay? If you see very clearly, can you raise up your hand, If you see clearly how this line shows up after plugging this inside here. Those can see, okay, those can see, Vilash, okay, Lawrence. Can see or not? Can see? Can Jethro, can see or not? You got good eyesight or not? Okay, behind Gregory can see it, Ryan can see it, Ting Hui can see it. Cannot, okay, just give yourself a little bit more. Wen Yu, 你看得见吗? Can you see? You can, Ethan, can you see the red color? Yeah, you just split up the n cube into, distribute the n cube into the three factors. Basically, you just distribute this n cube to the three factors. So the three factors will be n 6 over n, and then n plus 1 over n, then 2n plus 1 over n. By distributing the n cube on the denominator into the three factors, you see that there's a nice cancellation, and then you end up as this. Good. Okay, let me ask you, Howard, do you think that the area of the rectangles and the area under the graph from 0 to 1, are they the same? They're obviously not the same. Why aren't they the same? It's an overestimation because there are the so-called pockets of errors, right? These pockets of errors. Okay, these are the pockets of errors, right? So definitely the area under the ground from 0 to 1 and the total area of the rectangles, they are distinctly different. And how one is going to tell the class how he will perform a magic to make them the same. How one, please. How do you make the area of rectangles equals to the intended area? You're saying something, Hawan? Very good. So Hawan say, let n goes to infinity. Hawan says when n goes to infinity, meaning what? Meaning you have infinitely many rectangles. When you have infinitely many rectangles, the area of the rectangle, right, will get very close to the area of the area of the region under the graph. Why is that so? How will it continue? So how will say as n increases, these pockets of errors, right? These pockets of errors, they will start to diminish. And as n increases, these pocket of errors will diminish to nothing. So Howard says, as n goes to infinity, the total area, which I denote as capital A, the total area will tend towards the area under the graph, which we oftentimes do it like this. And let's check things out again. As n goes to infinity, right? As n goes to infinity, sometimes you can write this way, no? As n goes to infinity, A goes towards what? It goes towards 1/6 into 1 plus 0, 2 plus 0, and you get exactly 1/3. And you realize that this 1/3 tallies with what you have done previously. If you were to integrate this the usual way and then put in the limits, right, you find that it is also 1/3. It is not coincidental, no. It actually works like this. That from the summation of the areas of the rectangle, you can actually obtain the area under the graph. Interesting, right? Now, this area rectangle, right, that you see here is typically known as the left Riemann sum, because you're taking the area of the rectangle where the height of rectangle is on the left. Did I say left? Right, sorry. I say. She's right, I was testing you. Right Riemann sum. Because we are taking the height of rectangle on the right. Okay. I say. Right Riemann sum. Okay, so this is an example of the right Riemann sum. Now, so your understanding of Riemann sum is that of either the left or the right Riemann sum. In this case, it's the right Riemann sum. Moving on to the next page, I want to impress upon you that the Riemann sum is more than what you think. Okay, on the next page, right? If you are ready, I'm going to flick over the next page. Riemann sum on the next page, right, is you will see again very quickly that it is more than what you think. So this is a generic curve. This is a generic curve, okay? In this diagram, you are shown again rectangles. What is different about these rectangles and the rectangle that you saw in the previous page is, okay, let's hear from you, your observation. What do you think is the difference between this diagram and the diagram you saw earlier on? This time again, the height of the rectangle is not on the left or on the right of the rectangle. The height, that's one thing. Okay? So one thing you'll note is the height of rectangle is neither to the left or to the right. In this case, it's somewhere in between. That's one. What's the next difference that you observe when you? The width, right, may not be the same. The diagram is not obvious. The diagram has drawn all the width as being the same, but actually, we are supposed to see that in this diagram, the width of the rectangles need not be the same. That's why in your notes you see a delta x1, a delta x2, a delta xn. To tell you that the delta x or the width of the rectangles, they are not identical throughout. So this diagram and the other diagram differ in two things, no? That the height and the width. And then this expression that you see here. Okay, can you put a little I here? I think it's missing I, no? Missing I, xi. This expression that you see here, okay? This expression that you see here is exactly the equivalent of the total area of the rectangles that you saw in the earlier diagram. Just that because this time the height and the width is not the kind of height and width we were talking about in the right or the left Riemann sum. This is the case where the height is anywhere in between and the width is not uniform. So now you have a new expression. This expression, right, is typically known as the Riemann sum. Okay? And as we have discussed earlier on, the limit when n goes to infinity of this Riemann sum, there's xi here, no? There's xi there. The limit of this Riemann sum will give you the area under the graph if if what? If the limit exists. Yeah. If the limit of this expression exists, then it is actually so-called it will give you the area of the curve, area under the graph from one point to another point. There is something that I need to correct. I think that there's a little bit of a issue here. This one may need to be corrected. This one need to be corrected as this. Can you see this one? There's some errors. It's not n to infinity. Okay. In the example that we had just now about x squared, it is indeed the case when n goes to infinity. Because in the example, right, the width is divided by n, 1 divided by n. So when n goes to infinity, the width diminishes to nothing. But in this case, right, it should not be n, it should not be n goes to infinity. It ought to be this. Can you change this and write this? And I want you to appreciate how clever the notation is. In the limit, yeah, say. Someone say something. Oh, I was saying that. Sorry. This portion here, please replace it with this.
It doesn't matter, because even if the width is not constant, it will still be something over. I mean, your n will still be at the denominator.
You're right. You're trying to say that no matter what, as long as n is very, very large, this thing will diminish to nothing, right? But there's a little bit of problem, because if you choose to have one width, for example, right, in the interval from 0 to 1, if you choose interval from 0 to 1, if you choose, for example, that the last interval is always fixed at half, then you have issue. That might be issue. You know what I mean? So that n minus 1 rectangle plus only 1 rectangle here, and you fix those, then there may be issue. Right? But you realize how clever it is in the notation. In the limit, when the maximum width diminishes to 0. When the maximum width diminishes to 0, then naturally all the other width will also diminish to 0, isn't it? Very clever way of writing math notation, right? Don't you agree? Shibanya, is there something about James that you can tell me? I see you admiring James, you know. Okay. Alright. So I want you to see that this expression is the equivalent of the limit n goes to infinity for a in the earlier slide. If I have to move, okay, focus on this red bubble. I'm going to push up a bit to make you recall this other one. It's the same, no? It's the same as this expression. Same in meaning. In this easy example, when n goes to infinity, the width of all the rectangles, they do diminish to nothing. Likewise, in this more general instance, you find that the writing is slightly different. It's more general. Don't you agree that your knowledge of things gets expanded after hearing about this Riemann something? That is more than what you think before. That is, it's a more general form. Okay, now we go into some terminology, okay? Some definition. Class, you want to know that this definite integral, which represents the area under the ground from A to B, is defined, okay, to be this, and this summation that you see here is called the Riemann sum, and this integral, which you call the definite integral, is actually also known as the Riemann integral. When this limit exists, you will get the area under the graph. And if the limit does exist, we will say that this function is Riemann integrable. Okay, Riemann integrable if the limit exists. So these are just some terms. So lo and behold, you have to make the paradigm shift. You learned integration earlier on. You have understood what this was previously, and you know that through this integration, through this definite integral, you can find the area under the graph the way you did it. But all I'm telling you here is right here, okay? Actually, this has a more formal definition like this. So it's kind of, hey, you are seeing the other side of the definite integral. When you're first introduced to this notation, right, you have a certain understanding. Now you're seeing the same thing from a different side of the same coin. You know what I mean? And then later on, I want you to appreciate that even with this definition that you're seeing right now about the definite integral, those properties that you know about definite integral will still hold true. Okay, I'll make this statement. Let me make a statement again. Those properties that you know of about integral, right, or the definite integral, I want to assure that even with this new way of seeing things, those properties will also work for the Riemann integral. Yeah. Okay. So what you learned previously is not lost. In fact, it's not new. That you learned today, it's not new. It's just that now we are putting things in a proper perspective. That's how learning takes place, no? If you could recall, right, when you're in primary school, right, your teacher will say, never, right, -3, -4, don't have. You remember? Never have negative number. Then in year 1, you begin to encounter negative numbers. Then the teacher say, hey, never, square root negative number. You know what I mean? Then later in year 6, Sem 2, or in fact in lower year, you really encounter square root of -1 denoted as I.
Our entire life is a lie.
No, that's how things is like. If you to feed infant too heavy stuff, they may not understand, or it may not be good for the understanding. So sometimes parents will just lie to the kid to make them swallow some false food, and then hoping that in time to come they give them a better understanding. For example, children like to ask, no, where do children come from?
Oh dear.
My daughter ever asked. So parents will say, if you ask father, father say you can ask mother. Then ask mother, mother say you can ask father. Let me know. Then you out of frustration say, no, you pick it up from the street, like no.
Just ask both of them at the same time.
Okay. Anyway, class. So you want to understand that now we are seeing things clearer. Okay, as you age. If a function is continuous on a closed level, right away it is Riemann integrable on the interval. Some property you want to remember. It's quite useful. Okay. In the earlier discussion, right, we had the case where we drew the graph. I drew the rectangles, right? Drew rectangles, and then from rectangles I established a certain summation, and then take limit of the summation to give the area on the graph. Over in example 24, actually it's the reversal, no? If I were to tell you, say, take your hand and cover this. Then I'm gonna ask you back this question: Are you able to actually relate this to a definite integral? It means the reversal. And to do this right, the reversal. Okay, it means that given a summation like this, you have to do the reverse engineering to actually get back to the definite integral. You need very good eyesight, And I see that Mani is rubbing his eyes to clear his lens, his eye lens, to see clearer. So Mani, if I ask you, if I were to cover this portion, are you able to relate this to this now? Does it? Yeah. So Mani says he can see it, right? Mani says he can relate this one, he can relate this one to this integral. Okay. For this moment, let's pretend that this thing is cast aside for a moment. We want to find this summation or the limit of the summation by hand. Okay, by hand. Now after Hawen is Yen. Yen is not here. Okay, so Yen's buddy, Tae Yun. Can you show us or can you tell me how do I do this by hand? By hand, how? Right, you just write down, no? And what do I write, David? Okay, tell me what do I write here? Yeah, you're right. R. You say R, right? Okay, then from here. Okay, David, what's the formula for summation of R? And then how do you tidy up this arithmetic? You're trying to say this, and this gives you half into, okay, and then later on you realize that this summation, the limit of the summation, you realize that it is actually equivalent to this. You then therefore can say that this fella, because you're able to see the relationship. If you can't see, right? All you need to do is, you want to draw the graph of y equals to x. and you repeat the same steps that we had earlier on by dividing this into n rectangles. And then you find the area of each rectangle, and then you affirm that hey is the same. If you are not prepared to do it that way, you can then actually try to capitalize on this expression. No? It means seeing this reverse order. So this expression that you see here, is actually an attempt. It's an attempt to show you how you can write a definite integral into the limit of a series. So let's try again. Let's try. Say for this summation, for this integral, right? For this integral from 0 to 1, if you follow this guide, okay, this guide, your a will be actually 0, your b is actually 1. So according to this guide, right? How do we do it? Okay, on this guide, right? Okay, integral from 0 to 1 of x dx. According to this guide, it says limit n goes to infinity. The b is 1, so it's 1 minus a over n summation. It says k, right? K equals to 1 to n f of, okay, a is 0, 0 plus k, and then b minus a over n. And then upon tidying up, you get this 1 over n summation of k equals to 1 to n of, okay, if you tidy things out a little bit, okay, let me write this one more carefully. This is 0. So this becomes f of kn. And what is f of kn? Because the function is just y equals to x, so the value of f of kn is just kn. So it becomes summation of summation of just kn. And it's exactly that thinking. Whatever you do, whether you follow this faithfully or you could see it right away, you will make the same conclusion, right? Personally, I don't really follow this faithfully, this sentence faithfully. I typically don't. I typically just more or less can guess it now. How do I guess it now? I realize that typically, right, you see many of these things, right? Many of these things, it represents x. So if you have like this, right, 1 over n, 2 n, 2 n, so I know that therefore my function is fx equals to x. So I guess it. I typically guess it. But nothing stops you from trying to do it. If you're given a definite integral to go this way. The problem comes when when this function is not given to you. That will be an issue, like what you see in the next example. But the next example, they are so easy that you can actually guess. As I told you, this 1 over n, this 2 over n is just like x. So based on this observation, I therefore can guess that the function is, okay, Jun Shok. What function do you think it is? As I told you, this thing looks like x, you see. So based on this observation, I therefore guess that the function has to be x cubed. This one typically represents the width of the rectangle, right? This one represents the width of rectangle. and then it's 0 to 1. So if you got very good eyesight, like Jun Seok, okay, you can see immediately. Then working on this limit, it gives you an answer of 1/4. Lo and behold, what's happening here is you're learning another way to find limit. If you could recall, in chapter 1 when you talk about limits, right now, you can find limit by just plugging in. That's the easiest. You can do it by factorization. You can do it by conjugates. You can use the squeeze theorem. You have the sin x over x. You use the derivative definition. You also L'Hopital. Now this is another one. You see how they're connected? So now you can capitalize on definite integral to find the limit of, in this case, a sum. And for the second example, I am also almost sure that the whole class can guess what is that, Ethan, what is that? Yeah, you're right. Just simply square x. Simi. Allow what? You can write down the integral and okay, maybe write a bit more working again. Jethro, if that worries you, write a bit more working. to the integral, is it? If you have good eyesight and you get from here to here directly, yes, it's a good solution. Allow it. Yeah, allow it. You don't have to try to do it the way I showed just now, stating A, stating B, and so on. Don't have to. You can just, if you got good eyesight, and indeed you have good eyesight because you don't wear glasses. This kind of question maybe 2 marks only. Okay. Let's have Ryan. There are three expression here. Okay, it's a true and false question. So Ryan need to have a good eyesight. 26 part 1. To do or not to do? Is it a yes or is it a no?
Can I do part 2 and 3 first?
Sure. Is part 2 true or not?
Yeah.
You think part 2 is true, huh? Okay, Ryan say part 2 is true. Part 3 is it true?
Yeah.
Now Ryan is pondering over part 1. They are really two true, no? So you're right. It's 3 yeses. Ryan, you can qualify for next round of the AAGT. Yeah. 3 yeses is enough. 3 yeses out of 4, you'll get into AGT next round. So I'll see you on TV soon.
I think instead of AGT, I qualify for the next round of GC instead.
Okay. Alright, now we want to try to investigate why this should be true. To start off with, this question is a bit tricky, This question is tricky is because in this question, right, you have to divide into how many rectangles? Right, you got to divide into 2n rectangles. 2n rectangles. The trick is to divide into 2n rectangles. This is 0. Okay. Yitong, so what's the width of each rectangle? Right. So based on this, right, you can find the area of the first rectangle. What's the area of the first? Okay, I made mistake, no? I make a blunder. I have to redraw my diagram because it's not from 0 to 1. I was too presumptuous. And I said, the good thing is I'm doing on the digital platform. I can always redraw. Nice, right? Hey, by the way, next week for HBL, I will set you some work to do, so be on lookout. I know you're probably studying for your other test, but I will still set you work to do for HBL math lesson. So be mentally prepared that apart from studying for your test next week, what test do you have next week? Wow, very heavy reading.
Yeah.
Okay, let's start again. So you're given this diagram and you're drawn two end rectangles. What is the width of each rectangle? Is 1 over 2n, right? So therefore this point will be 4 plus 1 over 2n. This point will be 4 plus 2 over 2n, and so on. What is the area of the first rectangle? The area of the first rectangle would therefore be 1 over 2n. Yeah, 3 over 2n. I was kidding. Yeah. Luckily I can erase. Yeah, it's 3 over 2n. So there's 3 times 1. Don't worry, I can always make it bigger for you to see. Oops. I see. Nice, right? Yeah. Then it's this one. This one is going to be 3 and then 2. Right. Okay. Why is it 3? Because this interval from here to here, right, is a distance of 3 units. It's no longer 1. I was just help us do the rest of the question, right? So before I step out, what is A1, Chimaya? What's the area of the first rectangle? 1 over 2n times what? What's the area of second rectangle, Chimaya? Right, and this thing go on, and the last rectangle is A2n. Chimaya, what will it be? Simi. Okay.
It's 1 over 2n times the function, and 3 over 2n times.
Right, there's a 3 here. Oh, Shimaya, you and I are both wrong. She corrected me. The width is 3. Simi. I made a mistake, is it, Shimaya? Where is it? Okay, I think this should be correct. So by adding up all the areas of the rectangles, what do you see? Okay, you'll see that if you add up all the areas, right? If you add up all the areas of the rectangles, right? What you see is the total area becomes what? 3 over 2n. 3 over 2n squared of 4 plus 3 1 over 2n plus 3 over 2n squared of 4 plus 3 2 over 2n, and so on. And you realize that it matches this exactly. And by taking the limit, you will get the area under the graph. So for this question, the part 1, right? you can actually prove that the limit of that series is exactly the area under the ground from 4 to 7 of root x. You see, the problem is like this now. In this question, like they also give you these to look at. In the essence of this one, like in the essence of this function, right? It is actually quite sometimes may not be so straightforward to be able to come up with this. To be able to see that this one is equals to a certain for the integral, it may be quite hard, right? And if you try to use that guide given to you in that statement, it may not be easy to write out the way you want to. So I feel that the best way is just rely on your good eyesight. If you have good eyesight, you will see it. If you can't see again. And obviously, Lawrence and company is having some small conference there. Lawrence, what's that about? Is there something?
Briefing us about the
budget. Actually, yours sincerely had the experience of sitting in the Parliament House when the budget debate goes on. Why is that so? Because I told you, right, I worked for a Ministry of Finance before. I was the person in charge of the budget for Defence, Home Affairs, Judicature, the AG Chambers, the Auditor General's Office. And we were the people who would sit in the chamber, and then when they raise questions, we will rush back to the office to work out the facts and figures for the minister to reply the following day. So like first day of the debate, right, people filled the questions, right, we will work in the office. And very powerful, no, Michelle very powerful, no. We will tell all the head of departments all over the civil service to stand by in the office on it. They can't go home on them. You all didn't know. You know why? Because we need facts, right? We will call them out, they have to provide us immediately. No waiting on, no waiting. So a lot of the, say for example, Commissioner of Police, he'll stand by in his office, he won't go off, he won't go off. The perm set of all the different ministries, they'll stand by in the office, they won't go off. They're very powerful. Then when you hold meetings, right, it is the other ministry who will take the trouble to drive over to our office. You don't have to go to their office. No? It's very nice. To work for Ministry of Finance. Okay, anyway, so for part 1, you will realize that actually it matches. Okay, so in case you can't see it, you just have to draw a graph and draw rectangles. And the fact that Yu Tong can correct my mistake here and there, I think Yu Tong can see it. And because of this, Yu Tong will tell us why part 2 is so true, why part 3 is also true. Dun 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 dun. Create some music for you.
But part 2 is just part 3, except it's like 0 to 3 instead of 0 to 1.
Okay. You want to convince the class. So Yu Tong is going to convince the class that part 1 and part 2 are equivalent. Okay, Yu Tong, the stage is yours. Ethan. Shh.
Like if you start 4 plus x plus x.
You come to the front and address the class and convince the class. If you need my teaching instrument, I'll gladly lend it to you. Okay, Yu Tong is going to convince the whole class why part 1 and 2 are equivalent.
You start this for this, and you just convert it.
Whoa! 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 Whoa!
You have convinced me. I'm voting you for president.
Thank you. X plus 4 equals to x.
Okay, so she's trying to say, do it by substitution. So Yu Tong is saying, if you do it by substitution, you will see it. Okay, let's do it here again. Yu Tong is trying to say, do it by substitution. Let's try again. Let's take her cue, and we try to see that it works. Earlier on, it was integration from 4 to 7 of root x dx. So she's saying, let for example, u be 4 plus x. She's trying to say this.
Not like x equals 4 plus 4.
Okay.
U equals x minus 4.
Okay. Mind that. X minus 4. Right. So when x is 4, u is 0, 3. This is u plus 4. And then dx, in this case, you do a calculation, du dx is actually 1. Also dx du will later on be 1, it'll be 1. And then by this substitution, Yutong says we get this expression, which is just the same as this one, they're equivalent. And when I put back u as x, some people will fall off the chair, Okay, Yutong, how do you comfort the class and make them embrace this?
Like they can convert you.
Why is it that now I rewrite like that, Class, what's going on? So what happened here is, in the last line, right, some people will feel a little bit of a discomfort.
No, but because your O is just any other variables.
A proper name to say is what?
Dummy variable?
Right. He's right. Dummy variables. These are dummy variables. And she's right, okay, that they're equivalent, and that's why she said by using substitution, you can verify that these two are equivalent. Nevertheless, you could show that part 2 has the same expression like what you see here. You can do that also by drawing the graph of square root 4 plus x, and then go through the same process. You can do the same thing as well. Okay. With the heavier stuff that we just discussed, we are now moving on to something light-hearted. Remember, now we are able to confidently talk about Riemann integral, and the fear is always does it look like what I already learned before? And the answer is yes. Okay, like these properties that you know of in your good old days when you innocently learn integration. I want you to know and assure you that with the definition that you learned today about Riemann integral, those properties that you learned, they will still hold true. Ashad, do you know that the properties will hold true? Okay, thanks. Okay, your small converse there is distracting my my lesson. Okay. And then this one, Asha has something to tell us. Asha, what about this statement that you see on the screen that you want to say? Okay, Asha actually wants to tell you that this statement need not be true if you have infinite number of functions. If this is the summation of f1, f2 until infinite function. So what's happening in this statement is, it is basically a statement that says you can interchange. Okay, Ashad, go on. No, this one is true. But in the event that you have, okay, so what's happening here is, we are saying that this statement is true if you only have finite number of functions. But if you have infinite number of functions, Ashad will tell you that this statement may not be true. Let me say you cannot interchange. Go on. Yeah, you cannot just interchange integral and summation just freely like this. However, the engineers, the physicists, they just change and they don't care. Really. But the truth is, cannot.
Why?
It can be proven to be false at times if. Okay, he has more to tell you. So during tea break, buying a cup of water or buy a cup of drink, he will tell you slowly. In any case, class, I want you to know, be very careful. This statement is only true if the number of functions is finite. But when the number of functions inside the summation is infinite, you need very strong conditions before the statement can be true. And the conditions are, okay, you can read out in the book, I won't say, don't confuse you. So this statement is actually about interchanging summations with the integral operations. Alright, so be very careful. This statement have to be understood carefully. Then there's another property that you know of. You have seen these properties before, right? And the good thing is, even with the new way of saying definite integral, I want to tell you, assure you, that those things that you learn can be proven to be true also with the new way we look at the definite integral. It's going to be the same. Alright? And there are more. This one also. A to B, if you have something in between, also works. Like this simple question. Why don't you do it right now to just warm yourself up? Try. I'm almost sure that you haven't tried yet, most of you, because you've been too busy lately, right? Especially for Aditi, you went back to celebrate wedding, right? How was it? Good. Do you know the MTV called Chap? You know what? It's a very old song, but very entertaining, very entertaining. I like it, Chap.
It's very
So did you perform at the wedding?
no, not that song. But
Other song. Okay, in case the non-Tamil speaking people do not know about this performance, what is it? It's Hindi. Oh, okay. You should introduce to your class now. It's the MTV that I saw is very colorful, very nice to watch, Yeah. This year Deepavali, you should get the whole class to perform Chap on stage, And everyone dress up in the you play the MTV on the background and the whole class will on stage to do Chap. Wow. Then get Zhen Hong to be the star dancer.
oh my god. Let's go.
Okay, answer 27. Anyone has answer for me? Jethro, what's the answer? 27. 3 is it? Is it 3 or something? What is it? I forgot to answer it. Wait, let's see again. I'll get up right now. It's going to be 4 minus 12. Is it 4 minus 12, right?
Yeah.
So it's minus 8. It's minus 8. And then 1 to 2, right? 1 to 2 will be minus 1. Okay. 1 to 2 will be 2 minus 3. Money what do you get? Part B, you do that. Jairo, what do you get? Jairo, you were not in class the last lesson, is it? Were you in class? You were? Okay. Okay, so what is your answer for 27B? You get 1 lah?
It's 2 minus 1.
Alright, I was kidding. Wait, first.
Wait. Yeah, you want it.
Okay, my math failed me. 1 to minus 1. Okay. I feel so silly. Okay, it's 1. I was testing alertness. It's 1.
Yeah, very alert.
Okay.
It's okay, I made like at least 10 of those mistakes in this before.
Oh no. Let me see. Hey, wait lah. 1 to minus 1 to 2. Hey, I think there's something wrong, right? I thought it's 3, no? No, wrong. It's minus 1 plus 2. So it's 1.
Yes, you are correct.
Oh, Yu Tong is correct. Yeah, I was crazy. Okay, then there are other theorems that is quite self-explanatory. So there's something nice, no? Something nice that what you learned in the earlier year actually also works now that you see Riemann integral the right way. And then there's another one. Now we are into, okay. Can we read the first sentence together? In unison, the whole class. Should we read together? At the count of 3, okay? 1, 2, go. The first fundamental theorem of calculus. Why I'm asking you to read together is because when you read it, it's very high sounding, you know. And then you look closely at the result of the theorem, you say, hey, I thought I already knew this many years ago. Yeah, you know. There's also the first fundamental theorem of algebra. No? There is such a thing. Okay. It's to do with the roots of the equation. Right? Yeah. It's interesting that things you know last time, actually they got very high sounding terms for it. And a neat little explanation for you to do example 28 ABCD. Okay, it's just ABCD, no E. Can you give yourself that 2 minutes? 2 minutes. Viresh, what's going on? You're trying to convince Martin, is it Martin? No, Min. And Viresh said that this is ln of 2. This is, anybody has answer for me? Okay, Viresh, without thinking, without doing any calculation, what is this equals to?
It's a lot.
Okay, Viresh, give it another chance. Nothing better to do, just start memorizing all silly numbers. Okay. Part C. I mean for nothing, like just memorize. For part C, right? For part C, you don't have to expand to integrate, you know.
Isn't it the A plus 3 or
Right. And
I got 0. Oh,
right. And part D. I think it's 0. Yeah, I think 0. Oh. You know what? This stylus, cost me $125.
What a scam.
Yeah, it's a scam, you know.
Just for like tiny little eraser.
Huh?
Just for tiny little eraser. Yeah, that's the fact. It's a eraser.
Yeah. No, but you can't write without this, no. So it's a precious instrument to me. Okay, let's see. What is the missing word? Zhen Hong, what is the missing word? Zhen. Yep, say.
For part C, why exactly is it?
Ryan, you are given a count to 10 to agree that it's 0. Okay, I'm going to count again. 10, 9, 8,
I don't think it's
7,
Side.
6,
really only
5, 4, 3, 2, 1.
Happy New Year! Happy New Year!
0 minus 0.
I was in Finland on a New Year's Day. They also had fireworks. I was thrilled. I was in the big quadrant, Then you look up, wow. Actually, the fire was much more than the one in Marina Square, but I felt thrilled by it because it means home, is it? Yeah.
The pollution is also triple.
In where?
Because of fireworks.
Yeah, they do it there, they do it there and there. In Marina, they do it away from you, right? It can't go to the spot where they do the firework, it can't go. Yeah, it's true. Yeah, right. Yeah, you can hear, smell the smoke, it's true. Okay, Ryan, so you agree at 0 now? Okay, Ryan still does not agree. Let Ryan have some time to fill in his gap, Okay, Zhen Hong, back to you. What is the missing word? Yeah, right, Zhen Hong. Okay, let me do it for Zhen Hong again. When it's 1, right? It's going to be 2 minus 1 power 4 over 8 minus when it's 0. Right?
Oh, right.
Okay. Right, that's the turn. Okay. I'm going around to look at your question 30.